So this is the last class of chapter 2. So we're going to see the independence of events at first, and then we're going to see the sequence experiments. So here we're going to see the definition of the independence of events. So suppose that we have two events, A and B, and then if there is no meaning to A, there is no meaning of event B for A, then we are saying that they are independent to each other. So in this case, this is the probability of the event A. So in this case, B is given at first, and then based on this one, we have the event A. So if they have no meaning to each other, then the occurrence of event B has no meaning. That's why they should be same to each other. So that's why this relationship is based on the definition. Okay, so as we learned in last class, this conditional probability can be represented as follows because, so suppose that we have A and B, suppose B is given. So it means that this is our new sample space. That's why except this B, there's no meaning, okay? That's why we only consider this space. And then B is given, we are talking about the A. That's why we will take care of this one, okay? That's why this can be represented as P is given, and then we're gonna see only A intersect B. That's why we have A intersection B. So this is this one, okay? So in this case, we can have this relationship if they A and B are independent to each other. And then we have basic assumption which says that probability B is not zero at all, okay? And then we can do the multiplication of P of B in both sides, and then they can be eliminated. Then we only have this result and this result. That's why we have this result, okay? And then we can also say that this is true by the definition of this one, okay? So we usually use this notation if they are independent to each other. So when you want to check that two events A and B are independent to each other or not, then in that case you have to use this relationship. So then here, suppose that A and B are mutually exclusive. Then it means that we have A and B, and they have no intersection at all. This is called mutually exclusive. And then probability of A, probability of B are non-zeros, and then they cannot be independent. We want to prove that this is true. So we want to use the contradiction. It means that we want to make a statement which is the opposite of the given statement at first, and then we are saying that that is not possible. Then that is called, we have contradiction, okay? That's why we have a new statement which is the opposite of this given sentence. So then it means that suppose that A and B, two events are mutually exclusive as well as they are independent to each other. So by the equation of the independence here, so then we have this relationship, okay? So here we are saying that they are non-zeros. So this one is non-zero, this is not zero, okay? But since they are mutually exclusive, they should be zero. Then it doesn't make sense at all. That's why we are saying that this is contradiction, okay? So actually by mistake we skipped this slide. That's why let me explain this one, okay? So we have on, so we have this on, and then we have 4 balls, 1, 2, 3, 4, okay? 1, 2, 3, 4, and then 1 and 2 balls are black, so they are black, and 3 and 4 are white, so they are white, okay? So we have new sample space. In the sample space we have 4 balls, 1, 2, 3, 4, and black, white, and white, okay? And then we have event which says that black balls are selected. So then we have interest on these 2 balls. That's why we have 1 and 2 balls, and they are black and black. And the other event B is that we are interested in the even numbered ball. That's why we will gonna select this one and this one. That's why we have this one and this one, okay? So last event C, then we wanna select the ball where the number is greater than 2. That's why we wanna select these 2 ones. That's why we have these 2 results, okay? So our number of sample space is 4, and in these events A, B, C, we have 2 elements in every single case. That's why we have the probability of 4 over 2 for this one and this one, and P of C as well. So this is 1 over 2 because this equals 2 over 4, okay? And then we have to, so suppose that we want to check that A, B are independent to each other or not. That's why we want to calculate the intersection. So when you look at A and B, we are saying that, okay, we have one intersection. That's why we have one element which are existing in event A as well as event B. That's why we have only one case over 4 entire case. That's why the probability is 1 over 4. Then we are saying that this is 1 over 4 and this is 1 over 2, this is 1 over 2. That's why when you calculate this one, then you're gonna get 1 over 4 and they are same to each other. That's why they are independent to each other, okay? Then we want to check that A intersection C is independent or not. So in this case, when you look at this one and this one, you can easily see that they have no overlaps. That's why they have 0 probability, okay? Because they have no overlap. And then you want to check the probability of A and probability C. In any cases, they are all 1 over 2 and 1 over 2. When they are multiplicated, and we have 1 over 4. They are not same to each other. That's why they are not independent to each other. Okay. Okay. So then we want to generalize this this description. So suppose that we have 3 events A, B, C. Then we want to check that this is also true. Okay. So then we want to state that we have this relationship because all 3 events are independent to each other in our statement. This is called pairwise independent. Okay. So then we have new definitions. Suppose that this is D. The intersection of A and B is D. And then we are saying that PD, we are saying that here, this is based on the definition, what we have here. Okay. This is from this one. Okay. So this is D. And then we are saying that this is C of D. D is given, and we want to calculate the probability of the C. And this is P of C. So in the left-hand side, this is same with the P of D. And then we have P, C union D. Okay. And then this can be denoted by P, A intersection B. And in this case, P, A intersection B intersection C. That's why this is A intersection B intersection C. That's why this result. We have this one. And this is same with P of C, as we saw here. And then we want to do the multiplication of this one in here and here. That's why we have P A union B, A intersection B. And then when we have P of A intersection B, then we can get the elimination. Then we only have this one. That's why we only have this one. We have this result. And by this one, this can be replaced by this one. Then we can prove that this is same with this one. Okay. And then we can generalize this one more and more. That's why when we have n number of events and then everything is independent to each other, then the union of everything can be explained as follows. Okay. So this is the independence of events generalization. Now we want to see the sequential experiments. Okay. So sequential experiments means that in a given sample space, we want to conduct event operation several times. In this case, we have only one event. Okay. So suppose that, for example, our sample space is 1, 2, 3, 4, 5, 6. So this is dice tossing. And then our interesting event is the case where our number is the maximum 6. So this is our interest. Okay. So then suppose that we are tossing the dice 5 times. Then we have sub-experiment 5 times. And then our sample space is 5 times. Our outcome will be 5, will be the number of 5. Then our event is also 5. Okay. And in this case, the sequential events in every single trial, everything is independent to each other. Okay. That's why when you want to calculate the intersection of every single event, then we can just do the multiplication one by one. Okay. So let's look at the example. So we want to take the 10 numbers from the interval of 1 between 0 and 1. So in that case, suppose that so for the first 5 numbers among given 10 numbers, the first 5 should be less than 1 over 4, and the later 5 trials should be should be greater than 1 over 2. So this is our given condition. So for the first 5 trial, the number should be, this is the random variable, the number should be less than 1 over 4. And for the last 5 trials, the number should be larger than 1 over 2. That's why we have these events. Okay. So in this case, the probability in the one between 1 and 0, the case where the number is between 1 over 4 should be, the probability of this one should be 1 over 4. Okay, we have this one 5 times. Okay, so we have this one. So for the later one, between the 1 and 0, and between 0 and 1, the case where the number is larger than 1 over 2 will be just like this one, and the probability of this one is 1 over 2. That's why 1 over 2 probability will exist 5 times. That's why we have this one. Okay, so because they are independent to each other, that's why we can do this kinds of the multiplication. So this is in general, this is called Paranoia Trial. So in Paranoia Trial, we are performing an experiment once and noting that whether a particular event A occurs. If this occurs, then we are saying that we have the probability of the P. So if this is not occur, then we are saying that we are not having event A with the probability of 1 minus P. Okay, so this is called Paranoia Trial. So when the event A occurs, then we are saying that that case exists with the probability of the P. Okay, so when suppose that we are doing the experiment several times, so we are doing the experiment with n times, then we want to take the probability of the K success. For example, event A occurs K times among given n. So for example, we are doing the dice tossing. So then we are taking 5 trials, and then given this 5, we want to see the number 6 3 times. We want to see the number 6. So then then the probability is 1 over 6, and then we want to take the probability among given 5. We want to take the probability where we can see the number 6 3 times. Then it becomes 5 3 and 1 over 6 3 times, and the other 1 over 5 2 times. So this is the probability of the K success in n trials in Paranoia process. Okay, then we can have this kinds of the equation. So for example, so let me explain this one with one example in next slide. So this is example about the coin tossing. So we have one coin has tail and head and tail. Okay, so in this case, so we are tossing this coin 3 times. So we have this one, 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 this one. So we have 2 possible cases for one trial, and then we have 3 different trials. That's why we have 2 to the 3. So entirely we have 8 different cases. So we're gonna take the probability of the each case. So in this case, head, the probability of the head will be 1 over 2, 1 over 2, 1 over 2. That's why we have this one. And then suppose that the probability of the head is P in general, then we are saying that here we have P and P and P. That's why we have P to the 3. In this case, we have the head 2 times. So head 2 times and tail 1 times. Okay. In this case, we have head 1 time and tail 2 times. That's why we have head 1 times, tail 2 times. Okay. And lastly, we have tail 3 times. That's why we have tail 3 times. So in this case, they are same to each other. That's why we are saying that this is P to the 3, P to the 2, 1 minus P. In this case, we have 3, same thing. That's why we have 3P and 1 minus P to the 2. So in this case, we are saying that among this given 3 trial, we have had 3 times. That's why this is 3. So among given 3 trials, we have had 3 times. Okay, that's why we have 3 and 3. So in this case, 3 factorial, 3 factorial, 0 factorial. That's why this becomes 1. That's why we have only 1 here. So in this case, among these 3 trials, we have had 2 times. So in this case, 3 factorial, 2 factorial, 0 factorial, and then we have 3, 2, 1, 2, 1. That's why this is 3. In this case, 3 and 1. That's why we have 3 factorial, 1 factorial, 2 factorial. That's why this is 3, 2, 1, 2, 1. That's why we have 3 finally. So in this case, we 3, 0. We have 3 and 0. And then this is 3 factorial, 0 factorial, 3 factorial. That's why this is 1. So here, we are saying that the reason why we have 3 is that this is combinations. So we have permutation and combinatorials. In permutation, the ordering is important. That's why they are not same to each other. In combinatorials, the ordering has no meaning. That's why we can have head, we can have tail in the end, you can have tail in the middle, we can have tail in the head. But the probability should be same to each other. That's why we have the same probability 3 times. That's why we have this kinds of combinatorial solution approach or combinatorial computation. Okay, that's why we have this 3 times result. That's why we need this component. K is success with probability A, that's why we have P. This is not success case. That's why we are, when we have K success, then we have N minus K failure. That's why we have failure to achieve head. Here, this is the probability of the failure to achieve head, and then we have this amount of the failure. That's why we have this kinds of the probability at first, and then we don't need to care about the ordering. We can have the failure, any cases, any combinations in this trial. That's why we have these kinds of the multiplication. So then we have another view about this one. So in this case, this is a number of head. We do not have arrow. That's why it means that we only have tails. That's why we only have tails. In this case, we only have head at first, head one time. So head can be at first, head can be at the second, head can be appeared in the third trial. Then we have these 3 times of the trial. That's why we have 3, and we only have 1 head, and we have 2 tails. In this case, this is our typo, so this should be a head, okay? So in this case, we have 2 head, okay? Then we have the tail one time. Tail can be in the end, tail can be in the middle, tail can be in the head. That's why we have 3 different combinations. And then for each case, we have 2 success in to achieve head. We have only 1 failure to achieve head, which means that we have 1 tail. Okay. Lastly, we always have head. That's why we have only 1 case here. That's why we have 3 success. That's why we have a P to the 3. Okay. So this is the end of the class today. So, and then this is the end of the chapter 2. So during this week, I would like to post 2 or 3 more lecture recording in order to explain chapter 3. Okay, thank you, and let's meet together fairly soon.